All right, hello again, everyone, and welcome to this webinar. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra. My role is to help customers make progress with their quantum journey. And together with me today is Milan Kornjaka, research scientist from QuEra. Milan, how are you today?
Yeah, it's been great.
Wonderful. And today we're going to talk about machine learning and specifically quantum reservoir computing, which is a new algorithm that we're using extensively in our work. Just a few words about QuEra before we jump to the meat of the presentation. By the way, there's a Q&A box at the bottom of your screen. Feel free to submit questions anytime, and we'll do our best to answer them as we go. QuEra is the leader in neutral atom computers. We believe that neutral atoms is the best way to reach large-scale fault-tolerant machines for a number of reasons. Neutral atoms are perfect qubits, no manufacturing defects. We can make millions and millions of qubits that are perfectly identical. They scale very well. We and others have shown thousands of qubits on a single machine, and we believe that we can get to tens of thousands of qubits without requiring interconnect. They operate at room temperature, so no need for cryogenic cooling. And also, qubits can be shuttled, can be moved around, which allows us to implement novel error correction codes as well as more efficient algorithms. Of the neutral atom companies, QuEra is the leader. We're the only company with a publicly accessible neutral atom computer available 130 hours a week on Amazon Bracket. We're based in Boston, close to Harvard and MIT. And as you'll see, we work with customers in a variety of ways, including delivering on-premises computers. And we're hiring. Go to our careers page and look for many exciting career opportunities to join this amazing team. Earlier this year, we released a roadmap showing our progression from today's computer, Aquila, which is an analog machine that's on Bracket, to next-generation machines with increasing number of qubits, and more importantly, with logical qubits. We anticipate machines with about at least 30 logical qubits in 2025 and about 100 in 2026. Somewhere between those two times, some quantum computers will exceed the capabilities of classical machines for some algorithms. And as John Preskill put it when he looked at our roadmap, he said, ambitious but not crazy. So we're very happy to see that, and we're working really hard to make sure we're not disappointing anyone. How do you work with QuEra? One way is to purchase a QuEra computer. We've signed deals to deliver machines to the UK National Program and recently to Japan. We'd be happy to work with you as well, provide on-site installation and support, as well as community development. You can also access our existing and upcoming machines via the cloud, and that also gives you the ability to get support, mentoring, and direct exchange with our scientists like Milan and many of his peers. And we also work with customers for long-term collaborations to develop killer applications, to develop applications that make use of our world-leading hardware to solve real business problems. Some of that would take time, and we're patient, but we want to work with customers who are patient as well and making sure that their algorithms and their problems can be solved by our existing and upcoming computers. So with that, Milan, I'd love to move it to you, and please tell us about quantum machine learning and specifically about quantum reservoir computing.
Thank you. Well, it's been really exciting time here at QuEra, working both with our current generation of machine that everybody can access on the cloud, and this is the work that you can essentially check, but also looking forward to our future roadmap. So our topic today will be quantum machine learning, and we'll first try to answer a question: why would we think about quantum machine learning? What is the state of the art of the field, and what are our hopes there in terms of ultimately quantum advantage? Then we'll try to describe our current approach on our analog hardware, that is quantum reservoir learning. We'll dwell into our flagship results, which are essentially the largest quantum machine learning experiments to date, with up to 108 qubits, and potential for the so-called comparative quantum kernel advantage, which will hopefully what it is, and also talk a little bit of what sort of our collaborators are doing together with us with this algorithm. So let's start off. So machine learning today really doesn't need much of an advertisement. We know it's behind transformative technologies such as ChatGPT or self-driving cars, and it's, you can even say, unreasonably successful. And if I would, wanted to pick any reason behind this unreasonable success, that would actually have to be its data-grounded nature. So the data is what provides the power in machine learning. And given the success of the classical machine learning, it's obvious that the quantum machine learning will be critical for the future of the field. And where does the prospect for quantum machine learning lay? Well, as usual in the machine learning, we believe it's in the data. In particular, if you think about the types of data that we can throw at various types of hardware, there are distinctly classical and quantum data, as you can see here. And of course, we are talking about quantum hardware here, so the bottom row of this chart. In terms of classical data, that's the sort of data that we think about. But as quantum computers progress, we expect more and more explicitly quantum data coming from all of the hardware out there. So that's one kind of data where we expect quantum to actually be really good dealing with. However, there is also a possibility of an implicit quantum data that I'll try to introduce a little bit more further, which may look classical sort of at the start, but may have hidden quantum correlations. So here are the two explicit example of sort of data that we are thinking about. So in terms of explicit, the quantum data, here is an excellent experiment from Google at 40 qubits, where the tasks that this quantum machine learning approach showed was essentially classifying the features of quantum dynamics. So quantum dynamics was performed on the hardware itself, and then two types of machine learning were done. One of them had additional help of the hardware, sort of quantum post-processing. The other one didn't, and only the one with sort of quantum post-processing was able to learn this quantum dynamics. So this is explicitly quantum task. It's derived from hardware directly and processed on hardware successfully. However, we believe that there are many other hidden sort of types of quantum data. And this is a very nice example that we saw recently of an implicit quantum data, and it comes in the area of language ambiguity. So I won't go through this sort of paragraph, sort of leave it as a homework for our webinar participants. But if you analyze these sentences, and if you're trying to discern the meanings of these two pronouns, one of them one and one of them two, given the context of a sentence that can be changed by putting different words earlier, you essentially end up with Bell inequality. So it's quite fascinating that in a very meaningful language paragraph, there are quantum correlations hidden out there. And this is the kind of implicit correlations that we are thinking about. They're quite clear in this example, but really the hope is that there is more, and especially promising area that we might want to think about are materials and drag properties that we know ultimately stem from the quantum physics of the molecules. So obviously there is quite a bit of hope with the data, both explicit and implicit, but how do we deal with it? What about current quantum algorithms? And our state-of-the-art quantum algorithms that dominate theoretical and numerical explanations of the day are variational quantum machine learning algorithms. And these are, in essence, a quantum variant of a neural network. So in your typical neural network, you have your input nodes where you feed your data. You have the hidden nodes where the training power is hidden. as a sort of, and you have to get to it by adjusting a large amount of parameters, and then you have your outputs for your predictions. In quantum version, variational quantum version, you again input the data in a quantum circuit, and then you have typically quite deep layers of gates that have parameters, sort of hidden parameters, playing the role of the hidden nodes. Then you probe your quantum computer to get some outputs, and then you have to update the parameters of the gates in order to get the training power. Very similar to the classical neural network. However, optimizing the parameters of the circuit turns out to be quite tricky. In particular, you can end up with same problems as in the classical case, where you end up in various kinds of local minima, unoptimal solutions. However, there are even bigger dangers with quantum here. One of these are barren plateaus, where your sort of optimization landscape can be exponentially flat, and it forbids you for even going into the right minima, or your sort of landscape for optimization can be corrupted by hardware noise. That's quite dominant today. So with all of these sort of practical and fundamental costs, it's probably not a surprise that experiments with this otherwise ubiquitous variational quantum algorithms are very rare, small scale, and they usually don't explore quantum advantage potential. So the question is, we know there's potential in the data, and we can see that variational algorithms might be too costly or even have some fundamental problems today. So how do we solve this? And our answer is quantum reservoir learning. So before going to quantum reservoir learning, let's first introduce what's classical reservoir learning to start with. And the idea of it is fairly simple, and that is take our neural network and replace the hidden node layers with a dynamical physical system that we call reservoir. And this reservoir has complex dynamics that we probe throughout its evolution. It's influenced by our input data. And then once we get our probes to the dynamics, we typically do a very simple linear post-processing step in order to get our predictions or classification, for example. So this is usually done then in a gradient-free way in terms of the parameters of the reservoir. And this is the central part that we want to utilize quantumly. In terms of where is classical reservoir computing used, it's been quite important in the early days of machine learning, where we didn't have the power to train neural networks. But even today, using a complex dynamical system to predict other chaotic or complex dynamics, this is where it shines. And a very sort of successful example of its applications are in climate modeling, where in order to solve a climate model, you typically have to solve a large set of partial differential equations. And computationally, you're limited to, for example, very rough grids or rough times. However, if you have that sort of physical data and you feed it into reservoir, you're able to solve your problem very often on much finer grids. And this is where sort of this hybrid application of classical reservoir. So with that in mind, how does our quantum reservoir look? Well, it's a fairly simple architecture to get into, I would say. It consists of three parts. The first part is we take classical data, and this algorithm is general purpose. It can take a wide range of classical data. Here we have examples of images or a time series prediction tasks. That data is encoded into our quantum computer, in this case, QuEra, by encoding it into the parameters of the Hamiltonian that governs its dynamics. Some possibilities might be the shapes of the global pulses that act on all the atoms, varying the positions of the atoms according to the feature vectors of the data. We call it position encoding, or applying different pulses, pulse strengths on different atoms, again, according to the features of the data. Whichever encoding we take, the next step is the same. We perform a quantum dynamics on our qubits, and we probe that dynamics several times. The dynamics probes are then collected in terms of measurement expectation values of local observables, and these expectation values are fed into a simple classical post-processing step. Here we use linear to all these results, although it's modular, so it can be other sort of post-processing frameworks as well. And then we get our predictions or classification. And already you can see here, we don't need to optimize the parameters of the quantum sort of part of the quantum reservoir part. And we believe this is a huge advantage, especially over variational algorithms, because it guarantees our trainability. It means that we can save significant hardware resources. Also, the way we deconstruct algorithm with sort of local observables means that the algorithm is scalable, and we hopefully will also show that with our results explicitly. So let's go to some of our results. So we first start with simulations in order to prove what we sort of just described. And the data set that we typically use for that is as well-known MNIST data set, which are handwritten digits that you have to classify. And this is an example of explicit processing of the data. So for MNIST, we downsample our data using principal component analysis in order to fit it better on simulation or hardware otherwise. And then in this case, we position and code our data by perturbing positions of atoms in a 1D chain. And then if we run it in simulation, we can simulate it. If we run it on hardware, we have a possibility to parallelize runs on hardware in order to collect our data quicker by setting up multiple parallel chains that don't interact with each other. After quantum evolution, we probe it, we gather our expectation values and form our predictions by using linear support vector machine. And these are the results. Our sort of flagship result in simulation is that quantum reservoir reaches the problem threshold for MNIST dataset. Here you can see test accuracy on MNIST as a function of the number of PCA components kept, which is the same as number of qubits or QRC. And the top blue line here is a reservoir, and you can see it being of sort of equal performance with all of the other nonlinear classical methods, such as linear, such as 4-layer neural network, that fairly complex neural network for the problem, or a classical reservoir itself. So we are reaching the problem thresholds here. In practice, however, something that's very important to reach this problem threshold is how many measurement shots you take for each embedding of the data. This is an example. If you take 1,000 measurement shots, as you have to do on hardware, you would reach these thresholds. However, if you take less, your performance is limited by this number of shots. This is just a quadratic overhead on the sampling, but it's sort of fundamental for quantum machines, and we have to be aware of it when thinking about hardware performance. So let's go to hardware. So we implemented this proof of concept MNIST pipeline just described on qwEra. Here are the results on 3/8 digits binary classification, so just these 2 digits. And we reach very nice performance on qwEra, which is 93% test accuracy. And not only that, but it's sort of astounding that this is within 0.5% of exactly sample simulation. So simulation without any sources of noise included, we are just 0.5% from what our hardware does. In terms of overall performance of this data, this is about 2% below classical methods and also below exact QRC. And this is sort of a consequence of something that we just talked about, and it is finite number of samples drawn in experiments, in this case, about 100 samples. This effect of samples is also shown explicitly here for 10 class MNIST, on which we achieve 62% accuracy with the number of samples drawn. And you can see here on x-axis is the number of samples, on y-axis is test accuracy. And our test accuracy consistently increases as we draw more samples on the hardware. And our simulation suggests that we have quite a bit of performance left on the table if we sample more. So these are proof of concept experiments on MNIST. However, we don't stop there. We also look at other data types. In this case, we are looking at time series tasks. And in particular, this very common in literature Santa Fe time series task, which which is a laser intensity of a laser in a chaotic regime. And you can see here sort of these chaotic switches and sort of inconsistent amplitude of the laser that the goal is to predict. And this gives us a very intuitive look into how QRC works in practice. In this case, we encode the features of the time series through sliding windows into the shape of our global pulses. So it's a very natural encoding to think about. This is the shape of the time series, and this is the global pulse that we apply on the machine as well. And on the right-hand side, I have embeddings, so expectation values that we use for predictions that are brought from exact simulation and hardware on the bottom. And you can clearly see how these embeddings express the original data. For example, there is this big regime switch around 1080 on the time series, and you can clearly see it here both in simulation and in experiment. And you can also see pretty much all the other features of the time series. They expressed in sort of novel and nonlinear ways throughout our embeddings. And something that's very impressive for me, I would say, is that experiments really match a simulation well here. And the only additional thing you can see in experiment is sort of this noise, which comes from the finite sampling. So this is the stochastic noise that we talked about. So how does this work? And by looking at the embeddings before, I think it's not a surprise that experiments does well on the test set here. So here are the actual test outcomes in red, simulation, QRC in blue, and QRC on our Aquila in orange, and they match very well. We didn't stop only and looking at the prediction. We also use this time series data set to compare our encodings. We have these three encodings: pulse, position, and local, as we described. And something that we saw here is that the encoding that we suggest for our users, for example, is definitely the local detuning encoding, as it's the best performing in simulation. It's sort of equivalent to position encoding. On hardware, local detuning encoding is the best, and it's very close to the simulation results. We have sort of understanding of this when considering different kinds of hardware noise and how they influence data. What I would emphasize, the local detuning encoding here is what we suggest, and it's something that just appeared on Aquila a month ago. So feel free to try it out. This is a great use case for it, I would say. The next thing that we wanted to say is to really scale up our QRC experiments to the places where one does not usually go with quantum machine learning. For that, we use this data set of diseased tomato leaves. Here is an example of some classes with healthy tomato leaves and early blight and another tomato leaf disease. We encoded these images by just directly downscaling them in resolution and then encoding the values of each pixel into the bond strength of our 2D position encoding with Variational. So this allows us to really put a lot of qubits in there. And this is a typical hardware sample. And when we did that, we were, I think, astonished with the results. Here is the test accuracy in this data set as a function of number of qubits for many qubit sizes between 9 and 108 qubits. And as you can see, as we increase the qubit size, we have consistent scaling of performance, consistent improvement with increasing qubit number. And at 108 qubits, we are quite competitive with the classical methods here, even with a good nonlinear method. And to our knowledge, this 108 qubit result is the biggest successful quantum machine learning experiment to date. With some margin, previous record is the 40 qubit experiment that we looked at the beginning of the presentation. However, we didn't only stop at scaling up. We also wanted to ask a question. Well, we know there are potential quantum data out there or implicitly quantum data, and we know our sort of QRC embeddings at 108 qubits are potentially very hard to classically emulate. So I think you would be very hard pressed if you wanted to simulate our experiments at these scales. So can we join these do something together? Can we find sort of a potential prospect for where can this interactability shine? And for this, we applied a recent idea of kernel geometry and kernel labeling from the paper here. the basic idea is let's take two kernels, and kernels are in machine learning data transformations that essentially map data from one vector space to another and sort of changes geometry significantly. And this can be done even with two classical kernels, but let's consider a quantum and a classical kernel. And by knowing that quantum kernel is potentially classically intractable, we can expect that the geometry that it induces in the data, the kind of transformation that it induces, is very different from the classical transformation. And this paper gives us explicit construction of how to sort of use it by constructing a synthetic data set where if you take a standard, let's say, classical data set, and you just change its labels according to sort of the eigen direction in the kernel space where the quantum kernel sort of works the best comparatively, you can get a synthetic data on which there is a potential for something called comparative quantum kernel advantage. So in practice, we do this by processing our data set with half of our hardware samples in order to sort of perform this kernel geometry labeling procedure and construct now synthetic data. And then we take another independent half of hardware samples to perform learning and inference on this data. And here are the results on 3-8 binary MNIST dataset. Now, original result was that QRC had this 93% accuracy. Classical methods were like 2% above. However, when we do this kernel geometry construction and we relabeled essentially 2/3 of the data set according to that construction, we observe that quantum method is now 7% better. So this is quantum method on hardware. So we observe this really a quantum kernel advantage, as we call it, on hardware. And not only that, but if we look at the number of samples that you need to observe this advantage, it turns out that you only need about 20 to 50 samples to break even with a classical method, whereas previously you, for example, needed about 1,000. So this means that on these kinds of synthetic data that where a quantum method works well, where reservoir learning has some prospect for advantage, it also means it will require significantly less hardware resources. And I think this is quite an important message for practical use. So now going a little bit in a different direction. So reservoir learning is not only considered by us, but we are already working with our collaborators and end users in order to sort of apply it to other use cases, to real world data out there. And this is an example of an interesting work by Deloitte Quantum Services, where they sort of implemented our reservoir learning model on a smart factory data set classification. So this is sort of a data set made of images where your goal is to detect some factory defects presented in these images. And when they apply the reservoir in their original classical linear implementation, they had about 89% test accuracy on the data, and a reservoir in simulation, in this case, did fairly well with a 99% test accuracy. So a significant improvement over linear method that was previously in deployment there. So with all of this, with our sort of two main results with our quantum reservoir, and that is having done quantum machine learning on an unprecedented scale due to our algorithm and hardware, I would say that allow it, and seeing this potential for quantum kernel advantage, which means even though this sort of kernel advantage was done with synthetic data set in mind, with explicit synthetic construction, it does show that there are data sets out there, we just don't know how they look, where quantum can do better. And it can also do better on a very large scale. And I think when you combine these two, it's a very natural question to ask, what is the data where we can observe some sort of real world advantage based on this? And I think in order to find it, the way forward is to work together. So we are looking forward to working together and trying to see what use cases and data do you have, and do some of them fall into these interesting categories of implicit quantum or explicit quantum task. And I say quantum can hide in many surprising places, as we saw in a language example, and then hopefully our reservoir on large scale and with sort of this kernel advantage potential can help us get some significant results there.
Very good. Thank you very much, Milan. So there are indeed quite a few questions. So the first question is, can one run this today? I mean, is this on a computer that's available on the cloud, or is this on a computer that's hidden deep in the QuEra labs?
Yeah, that's a great question. I think it's really fascinating that you can run all of these experiments today as we speak. They are all run on our Aquila offering, which is an analog quantum computer that we have on AWS Cloud. And really, we've been running these as any user would by just submitting our tasks through a regular pipeline. You can try all the encodings and all the data sets that we have.
Now, you showed the slide where the test was done with 108 qubits and the quantum performance is approaching the classical one. You're teasing us. Well, what could you run it with more qubits? Do you expect that if you ran it with 150 qubits, for instance, then quantum would surpass the classical performance?
Yes, so that's of course a very natural question, I would say. So maybe first thing, beyond just the qubit number, this is still done with 100 measurement samples per data point, and sort of in a similar case as shown here. If you look at the same kind of data, this sample scaling, it turns out that even this 108 qubit result has still more steam in it. So if we sampled more, I strongly believe it would very quickly reach exactly 4-layer neural network. Now and I think it's also clear that you can trade either more qubits or more samples, and I think still reach that. So at 150, I'm also very confident that with this sampling layer, you would at least get there. Now, extrapolating further, we'll like to extrapolate and see this line going quite a bit more. But I would be careful there. I think there are some fundamental limits with what you can do with these kinds of downsampling of data. So it's actually more data limited in this case. So likely quantum might reach the same limit as the classical methods here, but I think that there are very easy performance improvements on the table that if you just run this experiment for somewhat longer, I think you can get quite a bit better.
At some level, this sounds magical, right? Because you take data, you downsample it, you put it in this quantum black box, you measure the results, and then you look at the results, you take the results and you do classical regression or classical machine learning on them. So what's your intuition? Why is it that quantum is able to extract these parameters and these values that are indeed helping making better predictions or better classification?
That's a great question. Maybe when we describe it, especially sort of from more general level, it does seem like magic. But I assure you, there are some very fundamental physical principles that are there inside of workings of the reservoir. For example, if you wanted to make a good reservoir protocol, a random sort of random ways to position the atoms or random sizes of pulses and so on would not necessarily work the best. But what we found is that there is this sort of physical regime, and that regime is very easy to describe, actually. It consists of all the energy scales in the Hamiltonian being comparable in size. So that means the scale by which you encode your data, for example, local detuning pulse here, the scale by which you mix your data, which is Rabi frequency for us, and the scale by which you entangle your data, which are interactions between the atoms, should be all of comparable size. And in this regime, where sort of quantum can sort of take the data and have a meaningful expression out of it, because encoding sort of comparable to other processes, it leaves strong footprint into our output. So this is how it works in principle. Additional consequences, I think that there might be some questions here as you see, is you don't need to do any sort of fine-tuning of parameters on the quantum side. You can just take this general principle of comparable energy scales, and as long as you're roughly there, your reservoir in our experience on many data sets and simulations and experiments will work well. So that means it's truly gradient-free. There is a sort of physical regime when it works well, and as long as you follow this physical principle, I think you can expect very good results. But there's no magic beyond there in a sense. You cannot just run any kind of recipe.
QuEra has a open source development environment called Blockade, which one could run on your desktop or on a GPU cluster if you have access to one. Can this algorithm run on Blockade? Could one experiment with it on a limited number of qubits before submitting to the live machine?
Yeah, that's a great question. It absolutely can. In fact, the results here, for example, which are our proof of concept results in simulation, were all done with our Blockade package. Here, I think we have results up to 15 or 16 qubits, depending on the data set. And depending on how much compute time you have, I think you can easily run, let's say, up to 25 qubits with our Blockade on reasonably sized data sets.
In the introductory slides, you compared the performance of quantum reservoir computing to four-layer classical neural network. In your opinion, how does it compare to state-of-the-art classical neural nets? I mean, how much are we showing quantum advantage here? How would you describe the quality of the results?
Yeah, so that's a good question. So I would say on these kinds of classical data, for example, MNIST here that was downsampled with PCA, what we are comparing to is sort of the threshold performance. When we say four-layer neural network, I think four-layer neural network really reaches the threshold performance given the downsampling of the data that we have. So if you take MNIST and only do 10 PCA components, you likely can't do much better than the 90%, for example, as Plot says here. So in that sense, four-layer neural network for this sort of simplified proof of principle task is state-of-the-art. Now, of course, there are much better results on the MNIST if you don't do the downsampling and so on. But within the confines of the data that we're giving, we believe this is the right comparison in order to sort of just prove the algorithm. So and just to be clear, we didn't observe any quantum advantage on the original classical task. As you see here, we were quite competitive with the classical methods. However, where we did observe certain kind of advantages on this kind of synthetic data. And we are showing here, in comparison between QRC and classical CRC reservoir, but we also did it against, for example, a Gaussian kernel that is trained, which is fairly state-of-the-art as kernels go. It's not the best and hottest from machine learning, but in terms of comparison, I think it's a pretty strong result on this synthetic data.
You showed a slide from the Deloitte webinar. By the way, I'll put the link to the webinar on the chat. And I think Deloitte tried this with a number of different data sets. They used this Smart Factory data set. They used open source medical images. They used, I think they did home pricing prediction in Kansas City. So it's time series. So in your opinion, are there data sets where quantum can do better? Are there specific features of a data set that would make it particularly attractive to quantum reservoir computing?
Yeah, so that's a very interesting question. I believe in our explorations with Deloitte, we might have shown some hints on a data set that was pharmacological activity data. It's a public data set from Kaggle on pharmacological activity. We did some hints there, although that data set is fairly small and sort of hard to conclusively compare performances of different methods. We did show some hints there of Reservoir doing at least as well as what's best classically possible. And I wouldn't say it might even be the case that it might be doing a little bit better there, but it's really hard to say. But for example, this is the kind of a data set that it will be quite interesting to look at, for example, pharmacological activity.
Why are we doing downsampling or principal component analysis? Is it to match the number of qubits? Are we concerned if we had more and more and more qubits, would we do a lesser degree of principal component analysis?
Yeah, so in this particular case, I think we just wanted sort of a simple sort of standard candle in order to compare our QRC against other methods, and also to be able to simulate this QRC readily with simulations. So when it comes to proof of principle, we use PCA because it gives us decently small feature vector sizes, which we can readily simulate, and it's sort of like a standard candle. And then we can also do it in experiment and sort of compare that both in simulation and experiments. When we go to some other data sets, for example, tomato leaves data set here, we don't use PCA and we use feature vectors of up to 108 features effectively. So PCA is not necessary. It's just something that helps us do simulations easier in principle. It also means you can use less qubits on the machine, but as you can see here, we can deal with quite large features. And this data set, for example, did not use PCA. For its downsampling, it just downsample images by reducing its resolution.
In terms of the number of samples that we run, so I think that on one hand, we have a training data set, and so we run each sample, but then we also run each sample multiple times. And there was a question is, what do we mean by the expected value? Why do we have to run samples, a single sample multiple times through the machine? And why are we showing that if we go for 20 times to 50 times to 100 times, we're getting better results?
Yeah, so this is sort of a fundamental sort of principle in quantum, and that is if you want to get results from quantum hardware, it's really from any quantum hardware, in any algorithm, you are dealing with stochastic noise. And that means in order to get a result with certain certainty, you have to measure repeatedly. Quantum computing is a stochastic computing model, so there's just something that's always there in algorithms, sort of this sort of stochastic component. In practice, that just means that if we measure for if we don't measure enough times, our sort of embeddings are noisy, and that noise influences performance. But this is a really sort of the smallest of overheads that you can have, I would say. This is a typical example of what does it do to our data. It sort of induces a random noise on our sort of expectation values here. It's very easy to deal with, and as I said, let's say 1,000 samples for many of the data sets here will suffice to not have to think about this at all, or even in terms of comparative kernel advantage, even much less, like maybe 50 samples, and you will get the result.
You mentioned 3 ways to encode the data into the quantum computer. I think one of them was through position, the other one was through detuning, and the third one through the excitation pulse sequence. Could you elaborate a little bit on these 3 methods, and is there one that we recommend more than the other?
Yeah, sure. So these 3 methods essentially use the programmability that we have in our hardware. So there is more programmability than what these showcase, but they essentially have used programmability as a resource. The first of these, global pulse encoding, is the simplest to understand, I would say, is that you take your data feature vector seen here, and you simply tune your pulse on Aquila to match that features, and that induces the encoding. The other encoding methods are a little bit more involved. In particular, the position encoding is not as simple as you would think. For example, you just don't move atoms according to the feature vector. You would ideally want to think about changing the interaction strength between the atoms according to feature vector. So instead of directly changing positions, you change interaction strength, and you essentially have to convert between the two. We know what are we have van der Waals interactions. They fall off as a 6th power of distance between the atoms. And we also want to keep some interaction even when the feature vector is 0. So you have to worry about this. And this formula is essentially going to take care of that. Local detuning encoding is a new feature on Aquila. And it's simply putting different local detuning values on different atoms according to the feature vector. Our recommendation is, having run all 3, is to go for local detuning encoding. There are reasons behind it. For example, pulse encoding, even though it's so simple to think about, has this problem of if we evolve our system for long enough, it will thermalize or even decohere slightly on hardware. And that means that some of the data encoding, especially in the later parts of the pulse, will be partially lost. And this means that in practice, pulse encoding is worse than local and position encodings. But we do recommend local detuning encoding or even playing around a bit with position encoding.
In your opinion, how would this work on superconducting qubits or on other types of computers?
Yeah, so if we think about other modalities, I think the principle of the reservoir is absolutely applicable to these modalities as well. However, the concrete implementation, I think, would suffer on some of the current digital devices. I think the sizes that we can reach here with sort of reasonable fidelities and expectation values at these sizes are still quite a bit of an advantageous. We're thinking about analog platforms and neutral atom analog platforms in particular. So, however, the principle can still be applied to pretty much all other modalities, but I think your results would vary. However, in future, as digital machines get better, especially with error correction, I think the reservoir is still the algorithm to explore because it's still a fairly frugal algorithm compared to variational algorithms. And it can have many, I would say, fun extensions in the digital world, sort of different versions of the architecture, versions where you, for example, have some mid-circuit measurements and they pump out the entropy out of your system. That's very interesting. Or the versions where you can process more data with a single run and so on. There's quite a bit there to think about in terms of digital reservoirs. Principle is applicable. I think your results today would vary, but this is not the end of the reservoir.
What is the typical process when a company wants to explore quantum reservoir computing with QuEra, other than sending an email to us on the website or sales@QuEra.com? What happens next once a customer is interested in exploring this?
So once we sort of, I would say, get together on a first chat, some things that we really want to think about first is what is the data that you have? What are its characteristics? Why would it be interested potentially with the reservoir? So the first thing that we do when we sit together is essentially talk about your data. The second thing is, if you have, for example, a team that's interested in exploring reservoir, if we have a quantum team, we have resources to share in terms of essentially Jupyter notebooks where you can explore, for example, different encodings or run the basic version of the reservoir. You can even explore, for example, classical reservoir and so on. So we have several resources that your team can check out. If you're working more with us on that end, we can sort of continue and try to prove the data set with the reservoir, typically first in simulation and then starting with hardware. Also, additionally, these are sort of the first reservoir results. Depending on what are your particular interests, we can also develop the algorithm together further. So that means going beyond the paradigms that we've shown here, which were, for example, fairly simple data sets and supervised machine learning. I think we can go even beyond that, even with the current reservoir. So these are some of the options.
We're getting a wonderful set of questions, and I don't think we're going to be able to answer all of them live. We'll do our best to answer them offline. But perhaps the last question is, how large of a data set would you recommend if you're running on a simulation, or how large of a data set would you recommend if you're running on the actual quantum computer?
Yeah, that's a great question. That's one of the considerations, definitely, at least especially in the short time. So if you're running simulation, I think you can fairly easily tackle data sets that are, let's say, up to 100,000 data points. Well, it depends on your feature dimension and the number of qubits that you employ in the simulation. And I think with enough compute and on, let's say, the 16 to 20 qubits, you can still hope to run a million size data sets in simulation. In terms of hardware, the need to repeatedly sample on hardware means that you are slower in processing the data. And that brings down this number to, I would say, up to 10,000 data points. So essentially, the need to, let's say, draw, 100 samples on hardware means that your total data set size is reduced by, let's say, a factor of 10 to 100 from simulation. But you can also, on hardware, you can run feature sizes, so the number of qubits that you wouldn't be able to tackle with simulation. So there's a trade-off there.
Milan, thank you very much for sharing your expertise with me and the audience. And thank you, everyone that joined this webinar. And make sure you subscribe to our newsletter to keep in touch and be aware of future webinars. Have a great day, everyone.
It's been great to chat with everyone.